shape. And geometry for our purposes here is used to represent shape and an element of size, right? Both together constitutes the geometry. There is a shape and there is size. And needless to say, this is the central essence of design, because this is what finally the designers get to communicate to everybody else who's involved in the product life cycle, right? And so one of the things that you will see, and why we have to go through a class like this, is because of Industrial Revolution in some sense. Because before that, if you look at any typical dwelling, and those days village was the unit that we had, these 5 crafts that you see in this slide were enough for every requirement to be met inside the village. You have the carpenter, you have the cobbler, you have the blacksmith, and the potter. And between these 5 people, 4 people, groups of people rather, you could meet any requirement for physical artifacts in the village. And this link, in some sense, was broken during the Industrial Revolution. Right? What happened in the Industrial Revolution? Industrial Revolution allowed people to actually, generate power out of steam. That was the big thing. But that power, was immediately harnessed to do a lot of useful things, right? I'm missing one picture here, and I will add it. I realize the weaver of cloth is missing here. That's why I first said 5 and then corrected to 4. I didn't realize that I was missing a slide. You need somebody to weave clothes for you too. So, but the Industrial Revolution, coming back to our story, the Industrial Revolution changed all this by providing enormous amounts of power, which basically took away a lot of the drudgery in the beating of the hot metal, right? In pulling and pushing of the loom, right? And rotating the wheel in the case of the potter, right? As it happens, the cobbler and the carpenter probably didn't get much out of this Industrial Revolution then, but later other things changed there too. But what this did was that it moved away the production sources to where water was available in plenty, which means the banks of rivers, right? And therefore, that movement, and the fact that steam was such an attractive, steam power became so attractive in increasing the productivity as well as decreasing the effort required, the manual effort required, that design and manufacturing became decoupled. See, earlier, the design used to be in the craftsperson's head, and the execution used to be, through their hands. So all the transmission used to happen through neurons inside the body. But for the first time, when the production sources and the production outlets moved closer to riverbanks in search of steam power, right, this link got broken. And therefore, design had to communicate with manufacturing. And that needed what we now call a product information model, right? Now, in the early days, there used to be very different ways of doing this. I will talk about that in a minute, but just to complete this slide here, the evolution in some sense led to mass production. Industrial Revolution led to mass production, and there people relied on what we now refer to as engineering drawings, right? So these were very formal representations of shape information that the people running the fabrication or the realization facility could understand. They could understand the form or the shape the designer wanted to build, the material out of which it had to be built, and to a large extent, it also communicated, maybe not explicitly, the manufacturing or the assembly process that need to be used. And the way they did that was through this specification of what I have written here as tolerance and surface finish. And I will try to illustrate that later, though this is not the focus of this class, but I would like to mention this point, so we will cover this. And I will tell you why we stop at this step here in this chart, because the rest of the story is going to be told in the next slide, right? But before we do that, what does a geometric model or a shape model do for you, right? What is it, right? The way we define it in this class, and generally people have defined geometric modeling, has to do more from what constitutes geometric modeling. The definition of geometric modeling is methods to define or represent or manipulate shape and other geometric attributes of a product or an object, right? Now, this is a definition from the perspective of the people in the field, right? Because they are the ones who are interested in developing these methods. But we in this class are people who want to use these, right? So for us, it's a shape model which communicates geometry and size and possibly some other characteristics that might be of interest to us. And we will come to that in a minute. But as a trailer or an example, right? Let me just show you a very simple shape that all of you will be familiar with, right? This. Now I can give you the geometry of this, and I can give you, size attributes of this. But the fact that there is a hole inside this cylinder is not explicitly available in the model. Right? That's what I meant by other shape characteristics, which may or may not be available. And we will elaborate on this as we go forward, but I just wanted to tell you what I meant by other geometric characteristics that may not be explicitly available. Right? So that's. But the other question of interest to us as a user of the model is, how good is the model? What is our metric for evaluating the quality of the model that we have been given, right? And the metric is very simple, right? Which is that whatever, stimulus you want to expose this model to, right? The response of this model to that stimulus, question or manipulation must be the same as what you would have got when you were exposing the actual object to that same question. Okay. If it seems a little abstract, let me give you an example again, right? So you have a model, let's not say what model, but some model of this object that I have drawn here on the side of this slide, a hollow cylinder, right? Now let's say you want to find out the weight of this cylinder. So the question to the model is, tell me the weight of this cylinder or the volume of this cylinder. Right? Now, the quality of the model that you have been given depends on its ability to answer this question. If you have a purely geometric model, presumably the model will also have some processes that can quickly compute the volume and tell you the volume. Right? But if it does not have material and material properties as part of its model, then it definitely cannot answer the question, what is the weight of the model? So that's an example of what we mean by the quality of the model. It depends on what you want to do with it. Right? If you want to find weight and it does not have material, then it is of no use to you. Okay? But if you only want volume, then a purely shaped model is good enough for you and you are happy with it. You don't need anything else. Right? And we can give other examples, which is actually there in the table below. For a minute, forget the column on the left. Just think of them as names of different types of models. Right? Some of you may know the difference between these models already, but just for the purpose right now, take their name as what it is and as a type of model. Right? So a wireframe in some sense is like a matchstick representation of an object. So a cuboid, will be represented by these 12 matchsticks. Okay, that's what the cuboid is. Now, this is good enough if you want to just make sure that, oh, I have a cuboid and it looks roughly of the size. If I click on these 2 points, it tells me the size of this thing. Just 1 second. Sorry. So where were we? Just let's go back to the. Are you still seeing the slide? I just moved back and forth a bit.
Yes.
Okay, sorry. Yeah. So if you just want to do what I just did, that make sure that, yeah, what you have designed or what you have modeled is actually a cuboid or something that looks like a brick and roughly it's 4 inch deep or 4 centimeters deep, then that's the answer you got. So the wireframe is good enough for that. So it's basically a quick, fast visual feedback kind of thing. Right. Now, the second task that I have listed in the right side of the table in the slide, right, are some actions. Now, some of you, again, may not be familiar with NC path generation, but essentially think of it as, generating the path of a tool that will machine this out of some a different shape. So let's say if I start with a shape that looks like this, and I want to get this shape out of that, right? Then I need to basically remove these material here, this chord of the material here, and the path that the tool needs to follow is what we call as tool path generation, the objective of generating the tool path. Now the question is this model good enough to generate this, right? Answer perhaps is no, because we don't know if the surface here is flat the way this assumes, or actually there is a small depression that is there. This is not a good way to show it. Let me say this. So for the same geometry, I can have it as a bump, or I can have it as a cavity, right? So it may show, let me just draw that separately here. If the wireframe looks like this, corresponding to the, so that's how the wireframe will look like. But it does not say what this surface is. So if I put my tool here, you cannot tell me, or the model cannot tell us whether this tool is just touching the surface, above the surface, below the surface, because that information is not there at all. You just know that there is a surface here bound by these 4 matchsticks, 2 bent matchsticks and 2 straight matchsticks. And therefore, to be able to generate information like this, where you want to keep the tool on the surface, you need some information about the surface as well, right? So that's the second part. Now, the third part is what I said about the volume, right? How do I find the volume of a part, or how do I, draw a picture of this so that it looks like a solid, right? Which is what it is. If it is a brick that I have modeled here, then I must get a rendering or a visualization of this that tells me that it is a brick. Or, like I said, the original question of a volume. Now, to get all that, I need more information about what is happening inside here. I must have some information about the fact that this is a solid and not just a surface, collection of surfaces. So then I need something like that. Now, density, if I want to find the mass, I need the density of the material, right? And if I want to do some planning about, say, processes, then I may want to know that there is a hole, and I cannot machine this hole before I get a good datum surface. Therefore, I need to machine the bottom surface first, and then this, things like that. All of that is clubbed under this thing called product model. So while some of this you may not be already familiar with, and it may take some time for you to sort of absorb this, think of it like this, right? That you have different types of models containing different amounts of material information, and the choice of that model will depend on what you want to do with the model. You may not want a product model. All if you want is a quick visual feedback. You're not interested in material properties when you're getting just a quick visual feedback. So the guiding principle then, therefore, is that the amount of detail that we want to keep in the model, the amount of detail that we want to receive from the model, will always be a function of the application or the kind of manipulation I want to do with the model. Right? And so we will see different kinds of models for different applications. In the course, however, we will not distinguish it on this basis. We will talk about each of these in order, right? But when you are using the modeling process, right, while you have access to all of these, you must use this judgment to figure out which one you want to work with and then proceed thereon. Okay, so, and the last bit, in computer-aided design, we call it the 3 R's of CAD, much like the 3 R's of learning that people used to propose very early on, many years ago, right? There are 3 parts, 3 aspects in CAD, right? When you use a computer tool. One is the representation itself, which is the mathematical model of the object that you want to either create, manipulate, or see, right? That's the representation. The second part is what we call reasoning. The second aspect is what we call reasoning. And essentially, this involves the manipulation part of it. So you may want to query the model and get some information out. So volume, right? Or whether these two parts are at least 5 centimeters apart. Maybe for your function in the part, you need that distance to be maintained between two parts. So you have to query the model and get that information, right? So that's the reasoning part of it. And lastly is the rendering part. The rendering is the feedback element in this whole computer tool. This is where the user sitting on this side of the screen gets feedback from the computer tool, what the outcome of all the modeling instructions ended up creating, right? So in this class, right, our focus is primarily on the representation part of things, right? At least the lecture parts of it, right? Your labs will include both representation and the reasoning part. And we will also cover a little bit of the reasoning part in the lecture module so that you understand what the capabilities are and what the limitations are. We will not probably go into the details of the sort of mathematical elements that go into the reasoning part, right? But rather understand what the limitations are so that your use of the tool becomes more informed. The last one, we are not going to be interested in it at all. I'm sure some of the design students may be disappointed there, but rendering is not the objective of this class, though we will talk a lot about the surface quality, right? But not rendering as a tool, okay? And the challenge here, as I said, and some of you are already aware of this, is that how do you take a 3D element, right? A 3D entity like the product or the object that you're designing and be able to show it on a flat 2D screen, and yet it is realistic enough for the user to understand and react and interact with that. That's the big challenge in rendering, but that's not the focus of this class, right? Our focus is primarily representation and to some extent reasoning. Okay. So I went backwards. Did I go backwards? Yeah, sorry. So now a little bit of how we have ended up where we are, and what motivated this whole thing, right? If you look at any development of technology, you will see that people talk about two things. One is the push factors, and the other is the pull factors, right? Typically the push factors, are from within the domain itself. I need a faster car, I need a better product, I need a product that is lighter, right? So forth. Or there is a new market that I want to address with a new product. Right? Those are all the internal things that push development. There is the pull factor, which is interesting things that happen in technology elsewhere. And the same way, this whole game of CAD, right, and computer modeling or shape modeling as we know it today, also had its share of the push and the pull factors. Okay. I have not put them here in any order, though. The first bullet, the digital computer and the numerical control of machine tool, are what we would call the pull factors. Right? These two technologies, like all good technologies, invariably come out of a defense effort. In this case, the efforts during the Second World War. Digital computer, all of you are aware of. It's basically at the time it was using valve-based transistors to sort of use machines to do computing. And later, of course, the whole thing changed by having solid-state transistors and ICs. And you see the whole revolution today that your mobile has more computing power than the computer that was first generated when all this came up. The second pull, the numerical control of machine tool, is no less dramatic, right? Though it is not as ubiquitous. Basically, the idea here is that for the first time, it was shown that a control program, right, or rather a mathematical program, can be used to control the movement of the machine tool in space, right? And that was a very powerful possibility when it first came, right? That you can drive the tool through an arbitrary path, right, based on some instructions to the machine tool controller. So those two things essentially were the, what we call pull factors. What were the push factors? The push factor was the war itself, actually, right? In the shipbuilding and the aerospace industry, there was immense pressure on both sides. But our interest in this case, the story is told by the winners, as always they say. the allies, the US, the British, and their supporters, was to build more and more planes and ships as quickly as possible. Right? That was the push factor. Now, why is that a push factor? For that, we need to understand how planes and ships were built in that era, right? During the war and just before that. So let's go and look at a picture here, right? I need to narrate it through. I don't have a sequential order of the pictures. But if you look at the fuselage of the plane, right, it has a definition of sections, right? And the way these sections are conceived by the designer are actually on either the floor of a large room or on the ceiling of a large room. Okay. So you have these large rooms where these elastic elements, the one that you see in the slide on the top right, a slightly wooden finish kind of thing here, right? This used to be called a spline. And essentially, the idea was that if you hang it in space, it'll leave it on the floor like that, right? It'll take whatever shape you ask it to take, and the way you ask it to take a certain shape is by using these clips called ducts, right? These black things called ducts to hold the spline in a certain location, right? In a certain way. And therefore, from the straight line, you pull it here and clamp it with this duct. And you push this back a little bit and clamp it with this, and leave them straight here and clamp it with those. So that's roughly the sort of idea. And you can see on the bottom left slide here, engineers, designers, basically, doing this on the floor by carefully controlling the location of these ducts and then seeing if they are happy with the shape of the spline. And that shape would match to one of these cross sections, okay, that you see in the top left slide here. And you stack this up, several of these, in a large room, right? Typically, you would do this and then assemble it on the roof, right? So you can either directly work on the roof by moving these ducts so that the shape is what you get, or you do it and then hang it on the floor, on the roof, or you leave it on the floor and wait for the next step of the process. Now, because this used to happen in large rooms, right? Otherwise, it won't work because these are two-scale splines and the shape is actually being defined directly on true size. They used to happen in these large rooms called lofts, and that is why this process ended up getting called lofting. Okay. So at the end of this lofting process, what you have are a series of sections like these, comprising of these elastic splines, either hanging from the roof or on the floor, so think of, laying out each of these on the floor. And so you have a series of sections like that. So I have a series of sections that go like this. I'm just exaggerating it. Obviously, your fuselage cannot be so varying, but essentially the idea, I hope, is clear, right? Now, these can either hang from, a beam on the roof with these ducts mounted at several locations the way you want them, right? Or they can be on the floor, in this case, they're on the floor with the ducts mounted wherever you want them to be. Okay. So that's what you have at the end of the lofting step. Now the designer's job is done. They have defined the geometry of the fuselage by a few key cross sections, right? I have drawn 5. In this picture, you probably see something like 12 or 13 on the fuselage. Okay. Now, after the designers are done with this and everybody has approved it that, yeah, this is the shape we want, the carpenters come into play, right? What the carpenters do is cut planks of wood to match these templates that people have created, to match these shapes that the designers have created. So they will actually take a wooden sheet and cut it to this shape, right? And maybe cut this to this shape and so forth, right? And so you have something like what you see in the bottom right here, where you see these wooden sheets defining these templates at various locations, right? So you stack them. Now these are very critical, right? They are critical for the next step, but they are also critical because they constitute the actual physical definition of the geometry that you are interested in. Later on, when you actually make a piece, these are the wooden templates that are used to verify whether the geometry is correct or not. In fact, if you go to HAL today in one of their factories which make some of the older planes, right, you will see these wooden templates made of balsam wood still lying there and still being used for verification and inspection. Okay. So that's it's a time-tested technique, and it's still used for the older planes and machines. So now you have this definition of the shape in the form of these wooden templates. And then your model makers come into the picture. So they'll come into the same room, arrange these wooden templates and, fix them on a jig, much the same way you see it in the bottom right here, right? And they will use a softer material like a plaster of Paris or other similar modeling materials, and essentially create the entire object, by filling the gaps between these templates, leveling them with their hand, making it smooth, and then create this shape, right? I have a picture. Maybe I can show you. Yeah. So you see this picture here in the that I'm circling my mouse with, right? That's the outcome. In this case, it's for a ship design, and pretty much like this here. So you think of it hung the other way around. You will get this as the output of the process after the model makers are done with it. Now the hard part starts, right? So you have this, sort of physical piece made out of plaster of Paris, and now the draftsmen come into the picture. The draftsmen with their protractors and their dividers and their scales will actually carefully measure points of the surface of this physical prototype and capture them in paper drawings. Okay, so you will have them think of the same plaster of Paris piece that I showed you in the previous picture, but assume that they're all filled here. So they'll go and pick points of this surface here and carefully note them with respect to some reference in a drawing paper, right? And since the shapes that they had those days were limited, they would either approximate this by a straight line or by an arc of a circle. Right, so an arc of a circle, another arc of a circle, another arc of a circle, and so forth, and then maybe a series of straight lines if they were all not too much varying. So that's what they would create, and they would do it at multiple locations. The designer did it, let's say here at 4, and here at, say, I don't know how many, 1, 2, 3, 4, 5, 6, 7, 8, or here at 12, right? They will create double or triple that number, right? So you may have three more in each of these. So you end up with something like 30, 40 sections where these measurements are done. Then these measurements are sent to the tool maker, who will then bang metal, or carpenter, who will then create a wooden master for the given shape. And that is then used to make the actual parts for the real planes and ships. And then those are assembled and then taken out. That's the whole process. Right. So clearly, there's a very cumbersome process involved in this whole cycle of tasks that need to be carried out. Multiple people are involved, and it takes it's laborious and it takes a lot of time. But there are two other problems with this that were the real actually push factors. One, of course, definitely was time. The allies were wanting more planes and more ships faster and faster. And therefore, any time spent on the design and corrections were not acceptable. What are the other problems? Can any of you suggest if there are any issues that you can spot with this whole process, other than the fact that it is painful and takes time? Anybody?
So the amount of space
that they need, you mean? What do you mean by amount of space? Can you clarify?
So this whole process of doing it manually, so the amount of area that you need is quite large.
Oh, yes. Okay. That is true. What you say is right. And it may be a bottleneck today, but let's just take it that was not a bottleneck then. Okay. Though it is a problem. I mean, I concede that point, but that's not the that was not the bottleneck then. Yes. Anything else that strikes you? one of the things that if you'll see is the definition of intent, right? What have the designers controlled in this whole process? The designers control the geometry of this final plane or the final shape, right? Only at these 8 locations or these 12 locations. That's the only control designers have. Elsewhere, it is controlled by the model maker. The way they sculpt the shape in between these materials by their hand. Somebody may sculpt it very smooth. Somebody may, sort of put a dip in there. The designer has no say or control on that. Right? Now, that is not a good situation for the designer to be in, where they are not in control of the overall shape of the object, but only at some key locations. That is one problem, right? That there is no control on the design. A model maker A, as I said, may make it, flat and straight between the two. Model maker B might give a small dip between the two, right? And these are all add up to variations in the parts which are not acceptable. That's problem one. The second problem is the storage of this information. See, finally, where is the design information held in this whole process? It is held in the form of these wooden templates. Like I said, these are used for inspection as well. That's point one. And two are these drawings that are given to the tool makers. Right? Those are the only 2 places where the design is actually recorded. Okay. So what's common between wood and paper? No, this should be easily answerable.
They perish.
They burn very easily. Yes. Right. And the first time the Germans were able to penetrate into the UK territory and bomb, right, they panicked basically that all their design information could go up in smoke in no time. Right? And there is no way that they can recreate these things. The only way they can recreate new designs, modification of old designs, is by having access to both of these. So that was another, anxiety factor that caused them to look for other ways to define the shape. Right. And there is one other problem with the wooden templates, which is that, it gives you different results in different seasons. Right. Wood, as you know, right, in a humid environment will have a certain geometry. In a dry environment will have a different geometry. Now, this is not good for industrial production. Balsam wood is definitely much better than most wood, and it doesn't deviate much. But in the industry we are in, aerospace especially, it can be critical. Right. So all of these factors that I just said, time, the cumbersomeness of the whole thing, the amount of people, amount of space that somebody mentioned, right? And more importantly, the fact that you are still vulnerable at the end of the day because your design information can just perish in no time. Right? All that led to this central question is that and coupled with the fact that the digital computer was coming into being, was the question that can we somehow represent this information in a computer, with the advantage being that one can reproduce it at will anytime one wants it. Okay, or a mathematical form so that it becomes easy to recreate and reuse. Right? And that was the central question that started this whole field of computer-aided design. And essentially, right, the question is that the designer is interested in prescribing only a few curves, right, but wants to get an acceptable definition of a surface so that they have control over the entire surface. Right, so they can keep tweaking this till they're happy with the surface as well now, and then pass the surface on to, for other processes. And given the nature of the game, again, people at MIT and the people at Boeing, which was one of the big, aerospace vendors then for the Air Force, they actually looked at this problem and they came up with techniques where you could define surface patches, which are defined by curves that lie on the surface of the patch. Right. So that's the first starting point for shape modeling using computers, right, or a mathematical form. Because one of the biggest problems with the forms that you have in the aeroplane, right, as you might appreciate in this picture here, is that you need to go through this exercise of actually manipulating, the shape locally to get the global shape that you want, is that these surfaces that constitute the surface of a plane or a ship, they do not have a mathematical definition. They are not what we call analytic surfaces, right? They don't have a single closed form expression that you can use. And therefore, this representation scheme came up where you define the surface using curves, and from those curves, we come up with the definition or a representation for the patches that form these surfaces. Quite independently from this, and probably a little later, Bezier was another designer come researcher in an automotive company. Renault is the company that he used to work for in France, Paris. And he basically had the luxury of getting a CNC machine in their lab. Actually, it is just an NC machine because that computer was local to the machine, not a central unit. And he had this grand vision that there should be the workstation that was next to the CNC machine could be used to define a shape, and that shape could be downloaded to the machine, and immediately out comes this piece machined in styrofoam or metal or wood that can then be shown to people and obtained. So in some sense, this was the first, at least conceptualization of your 3D printing kind of a model today, right? Your additive manufacturing or 3D printing essentially captures this, that as soon as you model it, you should be able to download it to a machine and get a physical prototype out. So that's the kind of demands or needs that were pushing the requirement of being able to represent shape using models, mathematical models or computational models. Okay. Now, remember that these are all still talking of surfaces. They are not looking at objects at all yet, right? They're all looking at surfaces where the volume gets filled in later, right? I mean, they are not worried about it. There was a parallel development which happened with again in the early 60s, right? And again at MIT, where Kunz actually was a person who also developed the surface patch representation scheme. He and another faculty member there, Dwight Bauman, they actually coined this idea of computer-aided design. And the idea is that there is a visual interface to the computer. See, the computer those days, I don't know how many of you are aware, used to work through these punch cards, So the information to the computer from the user, the program, goes in the form of holes punched in a sheet, and there will be a reader sitting next to the computer that will read those holes, figure out what the command is, and then pass it on to the compiler, and then it will compile, and then the program will execute. Right? But they can be conceived of this computer with a visual interface, a screen, which we can then be used to drive the whole product design process. Okay, and as it happens, even Sutherland was one of the PhD students at that time who actually came up with the realization of this idea. Right, and you see a picture of this in front of you, a huge computer with a screen, which is like your old CRT tubes, right? And you could draw objects on the screen by lighting up pixels, right? Lighting up small bits of the screen, and depending on what is lit up, that shape is what you get to see, right? So the whole challenge is then what kind of representation do you need to be able to, drive such a process, and that led to this whole. I don't think I have. That led to this whole look of a wireframe model, or solid objects, right? So it purely came from a display or a drawing on the computer screen perspective. So the easiest way to define an object, right, is a wireframe, so that the computer could be instructed to turn on the pixels corresponding to the line here, to the line here, to the line here, and to the line here, so that on a black screen, these green dots will be lit up and you know that it is a square. Right? Now, if it's a solid object, right, then there had to be some other manipulations done to be able to tell the computer to light these pixels, and therefore you can then make out that it is a cuboid and so forth. Right? Now, if you want to figure out where the hole is and where the hole is not, say for example here, if you also do this and here also you do this, and sort of you connect these things. Now this wireframe is correct, but it is very hard for somebody to see where the hole is and where the hole is not, and therefore they came up with this idea of turning on a lot more pixels, so that will amount to shading the face, so that immediately the hole becomes clear where the hole is. Right? So all of that was happening in the first two steps here, primarily due to the work of Evan Sutherland. Then in the late 70s, right, there was an office automation company in Rochester, right? Eastman Kodak and even Xerox was nearby, right? They funded a study of how to represent the kind of designs that they have in their office automation products. And the idea was to look them as solids and not as surfaces, because they were not interested in parts that looked like aeroplanes or ships, but they had parts that went into these boxes that would sit on people's offices and factories and do something useful for them. And out of that work came a lot of the early solid modeling effort, and we will look at the details of that. And so the sort of two fields, right, representing arbitrary or non-analytical surfaces and representing solid volumes, they both happened in parallel in some sense. Right? One was driven by the Air Force and the ship and the war and the CNC machine. The other was driven more by this whole field of computer graphics, or rather using a computer to design 3D objects and how to then represent 3D objects on the screen. Now, how did they come together? Right? They came together because of two things. Right? One, again, was that people wanted the whole process to be automated, not bits and pieces of that. Right? So you don't want the surface to be having a computer representation, but the rest of it not. Right? Then somebody has to capture that in a drawing and add the other pieces of detail from the solid part of it into the drawing. That didn't seem to be a smart way of doing things. More importantly, again, here was a pull from the industry. The numerical control process that we talked about actually evolved so that you could actually create very interesting shapes, right? You could create objects with very interesting shapes. So, for example, the skin or the surface of the mouse that you have, right? Now, that's also in some sense a sort of what one might call a sculptured surface, right? Much like the hull of the ship or the fuselage of a plane. Right? But then that sits on top of another solid object inside which other things are kept, and that forms a product. And so, it became important to sort of have both be in the same tool so that one could manipulate the surface as well as the volume that the surface used to bound. And that's how the newer CAD modeling systems started coming up in the mid 80s. And now, of course, you have the entire sophistication that I'm going to try and show you in the next slide here. So if you look at the evolution in the form of an arc, as you go clockwise, right? As I said, from a purely industrial production point of view, the engineering drawings were the first representation of choice. And to be honest with you, they still continue today, right? There are a lot of tasks in product design where the people who are responsible for the task do not appreciate or do not understand a 3D model, right? They would rather read a drawing and be able to make their decisions based on that. Right? The physical prototype was hand in hand, especially for the kind of domains that I mentioned: aerospace, ship, and now automotive. Right? The process that we described, of this lofting curves, and then the carpenters and the model makers and the draftsmen, in some sense, it still happens today for automotive design, right? if you talk to your colleagues who are working in these large companies that make motorcycles and cars, right? You still do a scaled model by hand. You know, you sculpt a model with your hand. That's what designers do, especially when they have to define the shape, the outer body, right? What is seen by the customer. Except that the other subsequent processes have changed a bit, and we will see how they have changed. You know, the steps of taking measurements of the surface and creating a drawing or a model, and then using the model further to do other things, those have changed. But that first step where the definition is created by the hands of the designer is still continued in a lot of design houses. Not all, but lot. And then you have this whole computer-based models where you have the surface model and then the solid model, right? These are the frames just below the prototype. So this is the prototype. This is a surface model where the blue one is the surface. I just show these as the elements that define that surface. And then you have a solid model, which is this right in the center at the bottom here. Now you have what we call as a product model, you know, where not only is a single part, but also the entire product, an assembly of parts can be represented, right? Along with the connections between those parts, right? In some sequence, and quite often information about material and tolerances and surface finish, etc. Okay, so that's where we are at now, right? We started from the Industrial Revolution somewhere here before this, and we are sort of, you know, come a full journey, and now we have this. As it happens, there are some newer representations that have come up that are challenging this way of representing the object as surfaces and solids, and we will talk a little bit about that as well. Okay, so I'm going to stop here right now and see if there are any questions or comments. Otherwise, in the next class, I will start with, as I said, the first part, which is the surface models. But before we talk about surfaces, we'll talk about curves and then surfaces and then look at solids and then the product model. Okay, so that's the sequence which we're going to follow, and we'll start with curves in the next class. But today, I wait if you have any questions. Or comments. Anything? Okay. If there are no comments, then I will stop here. You are free to ask me again. We'll do a recap in the next class, and you're free to raise some questions then, and then we will continue looking at representation of curves in the next class. I have added all the names I got from the emails that I received for the first meeting. If you know that I have missed somebody, then please ask them to contact me. And if some of you or those of you who have been added don't have changed their minds, then please again inform me through an email and I will fix this list. But otherwise, all further communications will happen on this particular team. I will be loading these slides. I mean, my goal is to do it before the class, but at least by the day the class ends, I will put it up under the files for this team. So you should be able to get a copy of these slides as well. So, okay, I will stop here and we'll meet on Wednesday at 2 o'clock. Thank you very much. Thank you very much. Yeah, sure.